Hello class, my name is Kevin Noice and I did my presentation on Ludwig Prandtl. This is my presentation. So the early life of Ludwig, he was born in Freising, Germany. And this is a cool representation of Göttingen, Germany, where Prandtl worked at a university for about 50 years of his life. He actually made some quite significant discoveries, but we will get to that first. Ludwig Prandtl was born in Freising, Germany in 1875. His father was an engineering professor, so his father really encouraged him as a young boy to really take note and observe the natural world, which allowed him to kind of excel through school. And he was a bright young pupil. He was top of his class in elementary school all through, and then he graduated and got his bachelor's in mechanical engineering in 1898. And then 2 years later, he received his doctorate in 1900. And he did his doctoral thesis on the lateral displacement phenomena, a case of unstable elastic equilibrium. So that dissertation was published in 1901, and then he became a professor in Göttingen in 1904. He worked at another university from from 1901 to 1904, and then he got offered a job in Göttingen in 1904, and he worked there until he died. So for about 50 years he worked there. So some major breakthroughs of Prandtl. So if you look here, it's Prandtl in the center, and then these are some of his staff that worked with him, and this was around 1918. So his major breakthrough happened very early on, actually in 1904 when he took the job at the university in Göttingen. So he pretty much was able to show the boundary layer effects on an airfoil. So he basically, in a paper, he went to a conference in 1904, and he did a 10-minute presentation because it was all the time they gave him. So he presented the boundary layer idea in 10 minutes, and it had such a huge influence on aerodynamics throughout the world. Still used today, and we talked about the boundary layer in class. So Prandtl basically was the guy who showed that two separate regions in the dynamic airflow over a surface, in which one region is friction dominant and the other has negligible friction. So you can see that in the picture here. So the inviscid flow goes over the boundary layers. Here is blue. And then with the blown up version of the boundary layer, we can see that the velocity will change based on the distance n from the airfoil. So he was able to show that, and we still use that today. So two regions of the airflow. So we got the inviscid flow, which is frictionless, and then we got the viscid flow or viscous flow, where there's the viscosity, and then the air basically sticks to the airfoil, which causes a lot of drag friction, which ended up being the most of the friction was caused because of the skin friction, which they thought was negligible before. So that was kind of silly of them to think that, because that's most of where the drag comes from. So then he also showed the boundary layer separation, which the boundary layer will separate from the airflow, and then underneath will create a negative downward pressure, which at a certain angle of attack will stall out the aircraft, essentially. So he was able to show that also. That was probably his main breakthrough. He did have a lot of other ones. So some of his other ones, some of the main ones, these aren't all of them because he did a lot, but he showed that wingtip aerodynamics were important to decrease induced drag on the airfoil and then the vortices. So he was able to show that. And then he also partnered up with another scientist, and they formed the Prandtl-Goulart transformation, which is a mathematical technique that allows solving compressible flow problems by incompressible flow calculation methods for fast subsonic velocities. So this was after World War I. He was studying the aircraft of the time, and he was able to, because there was an interest in supersonic flight, so he was able to help with a higher subsonic velocities, but not yet supersonic until one of his pupils actually took it a step further and helped achieve the supersonic. But he was also responsible for creating the proper shape for a supersonic nozzle that is actually still used today in wind tunnels, supersonic wind tunnels today. So that is it. And then here's a cool picture of the boundary layer and then airflow separation. So here's all the disrupted airflow. Here is the freestanding air creating downward pressure on the airfoil. And then you can see the separation point here where the flow is going. So this is all part of kind of what Prandtl worked on, and he's kind of known as the father of modern aerodynamics. So that was an interesting person to read about and learn about. So I hope you guys enjoyed this presentation and hope you learned something. Thanks.